The reason we looked at infinite limits is because this is the language we need to be able to understand vertical asymptotes. We've kind of talked about vertical asymptotes before, but we need to get an actual formal definition of these things. And here's our definition. If you look at this graph over here, at x equals c, there's a vertical asymptote. And I know it's a vertical asymptote because the limit as x approaches c from the left is infinity, limit as x approaches c from the right is negative infinity. What we're going to say is if the limit as x approaches c from the right of f of x, or the limit as x approaches c from the left of f of x, gives us either infinity or negative infinity. So we really just need one of those things to be either infinity or negative infinity. That's all it takes for f of x to have a vertical asymptote at x equals c. If we do a one-sided limit of f of x and we get infinity or negative infinity, f of x will have a vertical asymptote at x equals c. To actually find these in practice, though, there's a much simpler way to deal with this. We're going to say to find vertical asymptotes. First thing we're going to do, we're going to try to simplify our function. Then we're going to find where the denominator equals 0, I'll put in parentheses, and where the numerator doesn't. The numerator equals 0 and the denominator equals 0, not necessarily a vertical asymptote, could be a whole or something else. So let's see what we can do. I want to find vertical asymptotes of, okay, letter A, I want to find the vertical asymptotes of f of x equals x squared plus 1 over x squared minus 1. Well, I can't do anything to the numerator, but I can go and I can factor my denominator into x plus 1, x minus 1. That's going to give me x equals negative 1, x equals positive 1. Neither of these would make the numerator equal 0, just the denominator equals 0. So those are both vertical asymptotes, because those would give me something in the form a number over 0, which is really all that I'm looking for here. F of x equals x squared plus 10x plus 21 over x squared minus 9. I'd like you to take a moment and try to find the vertical asymptotes of this. I see that I'm discontinuous where the denominator is 0. That's when x is negative 3 and x is positive 3. But really, I shouldn't be doing this. I should be simplifying this first so I can get this down to x plus 7 over x plus 3. Now, I'm going to say that I have a vertical asymptote at x equals negative 3. What was going on at x equals 3? Well, because it canceled, there's a hole at x equals 3. One more. Actually, now this will work. F of x equals the secant of x. Don't really like secants. I'd rather turn this into a cosine. So I'm going to say this is 1 over the cosine of x. See if you can figure out what would make the denominator 0. Well, let's see. Cosine of x is 0 when x is pi over 2, and 3 pi over 2. But actually, there's more places. So at pi over 2, my cosine is 0. At 3 pi over 2, my cosine is 0. I can continue around the unit circle at 5 pi over 2. At 7 pi over 2, I could deal with some negatives. I could say negative pi over 2, negative 3 pi over 2. The best way to talk about this is to say that x equals pi over 2, and then, let's see, 3 pi over 2 is pi away from that. 5 pi over 2 is 2 pi away from that. 7 pi over 2 is 3 pi away from pi over 2. I'm going to say pi over 2 plus any multiple of pi. K times pi. Well, although k has got to be an integer, where k is an integer. Or if you remember the notation from Algebra 2, we could say where k is an integer. All this is saying is pi over 2 plus pi, pi over 2 plus 2 pi, pi over 2 plus 3 pi, pi over 2 plus 5 pi, pi over 2 minus pi, pi over 2 minus 4 pi, pi over 2 minus 7 pi. At any of those places, the secant of x would have a vertical asymptote.